Okay, I welcome you to this class. We have been discussing on force system resultants, reduction of the forces acting on the mechanical systems. Now, as far as today's topic is concerned, today's topic is important of all the topics in this force system resultants. As far as the mechanical systems are concerned, the mechanical systems are subject to a sort of loading, which will not be always a concentrated load, which will not be always in the form of a moment. But sometimes the loads are uniformly distributed loads, or sometimes the loads are non-uniformly distributed loads. For example, I can take an example of a cantilever beam. For example, we often see a cantilever beam. We often use a cantilever beam. As far as a cantilever beam is concerned, cantilever beam is that structural element which is fixed at one end. Cantilever beam is fixed at one end and it's free at another end. Okay, you must have seen this type of, this is called cantilever beam. This cantilever beam you must have seen beneath the slabs of your home. Okay, this is most frequently used beam in household constructions. Okay, so this beam is called a cantilever beam. As far as this cantilever beam is concerned, cantilever beam is the beam which is fixed at one end and free at another end. Okay, now this cantilever beam, if it has a slab over it, then the type of load to which this beam is subjected is that it has what we call as a uniformly distributed load. Uniformly distributed load means that the intensity of the load is fixed or constant from one point to another point. What does that mean? Let me first draw this uniformly distributed loading. The load acts at all the points of this beam. If you go through the entire span of this beam from this point, let's call this end as end A, from end A to end B. If we move from end A to end B of this beam, at every point on this beam, we find that the load acts, okay? And this load is called a uniformly distributed load in the sense that the intensity of the load is, we say that the intensity of the load is, for example, W Newton or kilonewton per meter. We write this as W Newton per meter. That means that if you go to any point, if you are here, the intensity of the load varying per unit length is W. If you are here, it's W. If you are here, the intensity of the load at every point of this beam is constant. We say that the beam is UDL. It is uniformly distributed load. Okay. Now, if the total length of the beam is L, for example, if the total length of this beam is L, okay, let's suppose that the total length of this beam is L, intensity of the load is W Newton per meter. If total length is L meter, therefore we can say total load on the beam, we can say that total load on the beam, total load is equal to, total load acting on the beam is equal to intensity of the load, that is W Newton per meter, W Newton per meter multiplied by the total length, that is L in meters. This meter and meter cancels, we get, therefore total load is equal to intensity of the load multiplied by length, WL. Okay, so in terms of meter will cancel, the units will be in newtons. Okay, so as far as this W into L is concerned, this is the total load acting on the beam. Okay, as far as this W is concerned, W is called the intensity of the load. Okay, intensity of the load, it is, it is like, if we are, it's called intensity of the load. If the intensity of the load at all the points on the beam is constant, we say that the beam is under uniformly distributed loading. For example, if you plot it along x-axis, I mean to say, if we say, let's suppose this is our x-axis, and we suppose that this is our y-axis. Let's take one more axis as our y-axis. Let's call this to be our y-axis, and let's suppose that this point is our x is equal to 0. This is our x is equal to L. The total span is goes from x is equal to 0 to x is equal to L. Okay, this is the total span. So this is our x is equal to 0. This is our x is equal to L. Okay, now how the load varies? At this point, the intensity of the load is constant. At this point, the intensity of the load is constant. At this point, the load is intensity of the load is constant. Now, if we move sufficiently close to this point A, let's suppose we take we draw a section out here such that this section is at a distance x, such that this section is at a distance x from end A. Therefore, how much will be the force acting in this area, which is whose span is x? How much will be the force here? The force here will be intensity of the load multiplied by x. Okay, W into x will be the intensity of the load. Okay, sorry, W is the intensity of the load. W into x will be the load that will be acting on a span whose length is x. Okay, because intensity of the load is W, Newton per meter. When we go to a distance of x meters, how much will be the load? That will be intensity of the load multiplied by the distance. That's W into x. So in as we go, so if you go to a distance x, if we go to a distance x, the load is W into x. So if we again, as the value of x keeps on increasing, the value of the load or the force keeps on increasing. That is F is equal to W into x. As the value of the x increases, as the value of the x goes on increasing, the value of the load on the beam also keeps on increasing. That means if you take a section out here, now if you say let's suppose this is our x, the value of x is more, therefore this load on the beam will be more as compared to the previous load. So it means if you draw the graph, if you plot the graph will essentially be like this. It will be a straight line, okay, such that the slope of this line, so we will say that this is x, this is y, and y varies with x as y is equal to W into x, intensity of the load multiplied by x, where this y represents the force. Okay, so but the, the load acting on the beam is increasing linearly, but the intensity of the load remains constant. Okay, when this happens, when the intensity of the load at all points on the beam is constant, when the slope of this load curve is constant, okay, because we know slope will be y by x, that's equal to W. When the slope of this curve is constant, we say the beam is under uniformly distributed loading. Okay, as far as these lines are concerned, these lines represent the intensity of the load, not the load itself. Okay, so we have, as far as in mechanical system we are concerned, we may be having beams which are subjected to loads having uniformly distributed loading or non-uniformly distributed load, as is the case here in this question. The beam is subjected to load, and at this end the intensity of the load is maximum. As we go from this end to this end, the intensity of the load keeps on decreasing. Okay, so this type of beam, we say this is non-UDL, this is non-uniformly distributed, this is non-UDL. The distribution of the load on the beam is not uniform. Okay, so this is a non-uniformly distributed beam. Now let's suppose when we talk about these distributed loads, when we have beams subjected to distributed loads, the load distribution may be uniform or it may be non-uniform. Okay, for example, this type of a beam, okay, which is fixed at one end and it has a roller support at another end, which we call as a simply supported beam. In this type of beam, if we are subjecting this beam to a loading such that the load of the beam varies continuously, the question is how do we find the total load on the beam? Can we replace this beam, this force whose intensity varies from x is equal to 0 to x is equal to L? As the intensity of the load, intensity of the load in this beam is varying, we want to replace this entire load by a single load. Okay, we want to simplify the loading condition for this beam as we have been doing for the previous conditions. Okay, the process and the procedure is slightly different, but the concept is the same. That is, we want to replace this force non-uniformly or the uniformly distributed force acting on a beam by a single force whose magnitude will be same as the magnitude of this force, as the magnitude of this force. Okay, so the force on the beam is varying from this end to this end. Okay, this force will have some total magnitude, total resultant. We will replace this force by a force whose magnitude will be same as the magnitude of this load, actual load. Number one. Number two, this beam, this force should be replaced by a force whose moment will be same as the moment which is produced by this non-uniformly or the uniformly distributed load. This is the question is same, that is we have to replace the actual loading condition by the loads. We have to maintain the magnitude of the actual load as well as we have to maintain the moment of the actual load. In order to do that, we have actually a concept that is what we call as the centroid of the figures, the centroid of the plane area. Okay, as far as this concept of centroid is concerned, we have a concept called the centroid of area, centroid of an area. The concept is same as the concept of, you have discussed the center of gravity. Okay, we are already familiar with the concept of center of gravity. As we have center of gravity, in the same way we have centroid of an area. Okay, when we talk about the center of gravity deals with the bodies whose mass is taken into consideration. Once you take those bodies into consideration, once you take areas into consideration, we define the centroid of an area. What is the centroid of an area? In order to before we define the centroid of the area, let's first of all understand how we simplify these problems, how we can reduce these problems. Then later on we can give the definition of the centroid. In order to make you understand, let me take this solved problem, or for that purpose I can take an unsolved problem, whichever I feel will be convenient for the students. Okay, now before, let me take this unsolved solved problem first. Okay, now as far as this solved problem is concerned, from this solved problem we will get the concept of how to solve these types of questions. After that we will discuss the concept of the centroid. Now whenever we have the loads acting on any structural element, okay, whenever we have the loads acting on the structural element, in order to determine, again I am saying the load is not a concentrated load. The load may be a uniformly distributed load or a non-uniformly distributed load, as we have here a non-uniformly distributed loading condition. Okay, this is a non-uniformly distributed loading condition. Now whatever be the loading condition we have, a uniformly distributed load or a non-uniformly distributed load, in order to find its resultant, always find out the area under the load diagram, or the area under the load diagram will give us the area under the load diagram will give us the resultant force. I mean to say, see, we have determined the magnitude and location of the equivalent resultant force acting on the shaft. There is a shaft, the length of the shaft is 2 meters. Okay, on this shaft load is acting, but load acting on the shaft is a non-uniformly distributed load. At x is equal to 0, there is no load acting. As we move from x is equal to 0 to x is equal to 2 meter, the intensity of the load increases. Okay, and x is equal to 2 meter, we have the maximum intensity of the load equal to 240 Newton per meter. The intensity of the load from x is equal to 0 to x is equal to 2 meter varies as W is equal to 60 x square. This is the equation of variation of the intensity of the load with respect to x. Okay, so W varies as 60 x square Newton per meter. This is the intensity of the load. Now this load is varying from x is equal to 0 to x is equal to 2 meter using this, following this equation. Okay, and at x is equal to 2 meter, the intensity of the load is 240 meter, where at x is equal 0, the intensity of the load is 0. Okay, now we have to find how much is the maximum, how much is the, what is the resultant load. We have to replace this non-uniformly distributed load by a single load. In order to do these types of questions, what first and foremost you will do, divide this entire area under the curve into small strips. Okay, we'll be dividing this area into small areas as has been done here. As is evident here, a small strip has been drawn here whose color is blue. This sky blue element has been taken such that this element is very small. The thickness of this element is very small and is equal to dx. Okay, so this total area under the curve has been divided into very small areas such that one area, thickness of one of the area is dx, and this area is at a distance x from end O. Again I am repeating, in order to find the resultant force, what we are doing, in order to find the resultant force acting on the shaft, what we are doing, we are dividing this load diagram into small strips such that the thickness of one strip is dx, okay, and this strip is at a distance x from end O. Therefore, at this, if the thickness is dx, if the length of this small strip is small, that is dx. Intensity of the load there is, say for example, w, as is given. W is equal to 60 x square Newton per meter. Therefore, how much will be the load on created, how much will be the load produced by this small area whose thickness is dx, okay. Well, again, as far as this strip is concerned, this strip we have taken very small strip, okay. This small strip, the dx is very small. So it means this entire strip can be, considered to be as, this small strip can be considered to be a rectangle. We can consider that this is a rectangle because we are selecting the value of dx is very small. Now again, this is a rectangle. This can be considered as a rectangle. Therefore, the area of this rectangle will be the small area. The area of the rectangle is dA, small area, that is equal to its width multiplied by length. As far as length is concerned, from here to here, it is actually